Hey everybody, welcome to CS302 assignment 1, and we're going to implement this mini solitaire game. Now, when I say mini, that means it's going to be sort of a simplified version of solitaire. So, typical solitaire, you have 7 piles of cards, and of course, the first pile has 1 card, second has 2 cards, sorry, third pile has 3 cards, and so forth. And then, of course, the topmost card is face up. The other cards below are all face down. So as you move cards around between piles, what will happen is the card that was was face down will be turned face up once you move cards around between piles. So let me go ahead and first just kind of show you the standard solitaire and how our version of solitaire will be slightly different than the original or the regular solitaire game. So let's go ahead and show an example of how solitaire is played. Okay, so this is sort of the standard, I guess, setup for solitaire. So here we can see we have 7 piles of cards. Now we're going to have only 5 in our mini version of solitaire. And then each pile, so first has 1 card, then we have 2 cards, 3, 4, and so forth. Only the top card face is revealed. The cards below are going to be turned over. So the way it works is you only can put 1 card on top of another card only if its number is 1 less and the color of the card is different. So for example, like right here, I actually could move this 8 of clubs to this right where this 9 of diamonds is because, well, 8 is 1 less than 9 and their colors are different, black and red. So what you can do is you can simply take the card and just put it right here. And then what happens is the card that was there below is going to now appear. That's sort of how solitaire works. So, and of course, we can move more cards. So in theory, if let's say we had somewhere on this board, we have, let's say, a 10 of clubs, then it's 9 and 8 both could be able to move to that one spot. But we don't have that scenario right here. So also in solitaire, you have these 4 spots right there where you actually can put an ace here. So I can put the ace over here and put an ace over there as well. And you can, of course, stack cards of the same suit on these. But again, not to make things really complicated. But that's really the whole idea of solitaire. Now, typically, you also have a deck of cards you can use to move around and put over here. But we're going to focus just on, really just on our 5 piles of cards. So I'm going to try to see if I can find other ways to move it around. Just so for example here, I can put this 10 of hearts right here where the jack would be. Now, of course, in our version of solitaire, we're not going to have a jack or a queen, or jack or a queen or a king. We're going to have sort of numbers 2 through 10. Just once again, to simplify the logic a little bit, this is our first assignment back from break. And essentially, in our version of solitaire, as you move cards around, the card below is going to be exposed. So you can move only 1 card, or you can move multiple, a set of cards can be moved onto a spot. And then once all of the cards that are face down are all face up, the game ends. So I'll actually show some actual test run of the program later on, but that's sort of the idea of solitaire. So of course you can look up the solitaire rules and you can play around with the game a little bit just to understand or get immersed more in the game. But let's go ahead now, just go into the actual data structures you will have to implement for this assignment. Okay, so let's go ahead and first discuss our data structures. So we're going to implement a linked list class. And I chose linked list because, well, it's going to be a little bit of an easier, well, not really easier, but it's actually more efficient runtime wise to use a linked list for this implementation. So for a solitaire game, it has a better runtime to use a linked list versus using a dynamic array or a vector. So we'll have a linked list type. So we have our struct node. So of course, every node in the linked list will be a node, and we have a data, and then we have our pointer. So we're going to have a doubly linked list. So we can travel 2 directions. You can go left to right or right to left. And we have some data stored in each node. And of course, it'll be a template or a class template. So we'll go over what the type will be later on, but it is up to you how you want to implement the linked list or what type you want to use. But I'll go over an example of where it might be a bit more handier to use sort of a custom type instead of a primitive type, but we'll get there a little later on. And then we have our 2 pointers, head and tail. So we're going to have a doubly linked list with a head pointer that points to the front node and a tail points to the end node. So pretty simple. So after that, we have our iterator class. So the iterator is going to really pose as sort of a pointer, if you will. So in main, you want to be able to traverse a linked list with a flexibility similar to how you would traverse a linked list using a pointer. But remember, we want to keep pointer data hidden because if, let's say, somebody used this this data type, LL, linked list, we don't want somebody else to accidentally break the linked list and be able to have direct access to pointers. So the iterator class is going to be sort of the, I guess, the middleman. It's going to help us be able to traverse a linked list flexibly, just like a pointer, but not a pointer. Now, this entire linked list class is actually, not linked list, iterator class is implemented for you. Everything is already there for you. Now, I do have documentation where I wrote in this PDF that explains what every function does, so that way you understand what's going on, but you will not have to implement any of these. They're all given to you. They're all very simple functions. So let me first just go over just the overview of what the iterator does. And of course, I'll go over an example here on OneNote that will show you how to use the iterator. But let's first sort of go through this really quickly. So the iterator class has this pointer node star current. That tells the iterator which node of the linked list it points to. And then a friend class, that implies that within the linked list class, if I were to actually create a local iterator object within the linked list, I'd be able to access the current pointer. Also, if I have an iterator object passed as a parameter into a linked list function, making it a friend class will allow the linked list class to access the private member of iterator. So that's kind of a benefit, I guess. So we have our 2 constructors. Our default constructor is going to just simply set current to null. Our other constructor sets current to whatever we pass into it. That passes some pointer, and it will assign that pointer into current. The star operator is going to be our, I guess you can call it our dereference operator. It's going to retrieve the data field of the node that the iterator points to, similar to how pointers work. It's not a pointer, but we're trying to somewhat emulate a pointer. So star means it will extract the field, the data field of that node. And then we have our plus plus minus minus operators right there. So the plus plus operator is going to simply just move the iterator one node to the right. And then minus minus operator is going to move the iterator one node to the left. Now, we have this really weird syntax where I have, if you notice, we see iterator operator plus plus int, and then we have iterator operator plus plus with no parameter. Now, what this actually is if you have the plus plus like right here with nothing in the parameters, this plus plus operator is going to be a prefix operator. So in 135, you might have learned about what prefix and postfix operators are, but that's the idea. The plus plus with the int after makes this plus plus operator a postfix, which means that the plus plus appears after the iterator. The prefix, the plus plus appears before. Now in reality, there's not too much of a difference, but it depends on how they're used. But really, for the most part, it doesn't really make any difference. But if some of us are more advanced or have a better understanding of prefix and postfix operators, you can use this accordingly. But in reality, it just means that a plus plus in this case appears after the iterator, and this plus plus appears before the iterator. But there actually is more than just that as a meaning. But I guess for right now, you can use either one as long as you use them responsively. So if you have, let's say, if you have a line of code all by itself with plus plus somewhere used on the variable, then if it's a prefix or postfix, it won't matter. But if you're using that with other operators as well, then there could be a problem. So I would just suggest, to be safe, if you use a plus plus or minus minus, only have that operator used all by itself on that line. I'll explain that in a little bit when I go over the actual examples of how iterators work. Okay, so and of course we have our comparison, which we're going to simply use these equals equals not equal to simply compare if any two iterators point to the same node or they don't point to the same node. So you have to write the actual functions. Iterator class is given to you. I document iterator as well right here, but I will, of course, in a video, I'm going to go ahead and show an example of how you can use iterators so it gives you an idea. I also have some code in the PDF you can read through as well, but I will go over it here in the video as well if in case you are more of a visual learner. So now let's finish up the rest of the linked list class. And of course, I'll probably have to go over in more detail some of the functions, but I'm going to first just sort of run through all of these. So we have to implement the linked list class, but I do actually implement some of the functions for you. So here's our default constructor. This constructor simply just sets the head and tail both equal to null. Then we have to write our own copy constructor, our assignment operator, and our destructor. This is going to be mostly used, so on the auto test, I have a rubric category for deep copy tests, deep copy and memory management tests, and we're going to be using these members for that. So you have to implement the deep copy constructor and deep copy assignment operators. So of course, maybe you can go back to your CS302 notes to refresh what these actually mean. And then we have our destructor, which will, of course, will deallocate the linked list. So again, this should be relatively a recap from CS202. I believe these topics are definitely covered in the object-oriented C++ class, so I think we're okay there. Then we have our begin and end functions. These are also written for you, but I'll also go over how they're used. But really, you can see here a begin function returns an iterator whose current is assigned to the head pointer. As you can see here, I do create an iterator object and return it. An end function returns the tail iterator. So essentially this is a way of returning a head and tail pointer, but we're kind of masking that pointer inside of an iterator. Then we have tail insert. Well, this is going to be just simply to do our standard tail insert to a linked list. So we're going to take some data value and we're going to insert a node to the back of the linked list and assign this parameter value into that node's value. Pretty standard. Now, these two tail inserts are going to be very bizarre. So I think the hardest part of this assignment will be these two functions. This is kind of where a linked list has a benefit over a dynamic array or a vector. So these two tail insert functions, you're passing an iterator. You're passing an iterator that points to an existing node. And you want to simply just tack it on the end of your current linked list. I'll draw an example out that will help you see how this works. I'm probably not going to spend too much time going over the copy constructor, even this regular tail insert. This one's actually pretty standard from CS202. I'll probably spend more time on these two tail insert functions and the remove function as well. Now, this remove function right here is also it's not going to deallocate, it's going to simply cut off a node off the linked list. And I'll explain what that does. Now, this head remove function right here, this will be your standard head remove function on linked lists, just like in CS202. So in 202, how do you remove a node the front of your linked list? So you can of course use that nodes from 202 to just simply deallocate the head node from your linked list. That's pretty standard. And of course, isEmpty is written for you as well. It returns true if the list is empty and false otherwise. So I'm going to give you the header file for this assignment. I'm also going to give you the linked list implementation file with all the functions that you have to actually implement. So all the functions that are already implemented right here in this header, I'm not going to create a function heading for those. So anyway, let's go ahead and now first talk a little bit about iterators before we go into the more complicated, these funky tail insert functions and this funky remove function. Okay, let's go ahead and now discuss iterators in this next portion. Okay, so consider the following picture right here. We created this linked list, and in this particular instance, our linked list will be integers. So each data field of each node will contain some integer data. So I create this list, and I say list.tailinsert7, then tailinsert6, then tailinsert1. So we have the following linked list after doing 3 tail inserts. So these tail inserts right here are pretty standard. You just go back to your 202 notes and you go over how to tail insert. It's very simple, so I don't really think there should be too much complication with this. So now at iterators. So right there you can see right below I actually define iterator object right there. It's a little bit of a strange way of defining it, but the idea is that we have a nested class. As you can see on this side, we have this class linked list and we have a class iterator defined within linked list. So the idea, it's a nested class. So the iterator cannot exist without a linked list. This is sort of, I think this is actually composition, and aggregation is more loosely defined. I'm not sure about the two words, but this is sort of the very extreme version of composition. So without a linked list, there's no iterator. So we have to, of course, in order to access iterator type, we have to first go through the linked list class. So linked list followed by this scope operator, and then we have the class iterator defined within linked list. And then it is going to be our data type. So I'm going to maybe put this here at the very top. So we'll have, let's say, it, this object. And I'll put a little block over here to denote this is going to be an object. Then we have, I guess, this current field, one of the fields that are stored within this iterator it object. Now, if you want to be able to traverse the linked list, what we can do is you can say, well, it equals lst dot begin. Now to recap, what does the begin function do? Well, looking at the PDF, it returns some iterator object, and that object's current will contain head. And then that gets returned, and then we're going to assign that iterator into it. So it's current, well, will point right to that node. So the idea is we either set, so we can either do it equals the list object dot begin, which will set the iterator to the front node, or if I were to have said it equals lst dot end, well, in that case, what would happen is this iterator would point to that node. So it's up to you which one you want to do. So I'm going to go ahead and just be, I guess, left to right is kind of more natural, I guess, to us. So I'm going to just go with the iterator it equals lst dot begin. Okay, super. So now what I can do is if I were to do, let's say, I'm just going to simply say cout star it. Right here, we're going to actually call the iterator's operator star function. So this function right here, that gets called right there. So it returns the data field of the node that it points to, or it's current points to. So right now, it points to this node right here. So star it returns the value 7. And then, of course, here we're going to simply output 7. We don't have to output. We can do other things. We could compare. We can do things with it. But for now, we output. So we have 7. So again, not really too different. Very similar to how, pointers so far. But there's no pointer being exposed here, but it has similarities to a pointer. Now, if I do it++, that's going to call the postfix operator. And that plus plus means, okay, move it to the right by 1. So IT points to that node. Now we're going to update IT. Its current is now going to be assigned to the next node. That's what plus plus does. So it's now if I were to again cout star IT and L, well, now it's going to output 6. Because the star operator is going to retrieve the data field of the node that the iterator points to. Now, of course, you can, could do plus plus IT as well. That's going to call the prefix operator. Now, there is some difference between them, but as long as if you were to just all by itself on one line do this, then there's basically no difference. It's only if you do some bizarre stuff, then you might have difference. But I would just say, unless you're not too comfortable with the difference between pre and postfix operators, I would just suggest have the plus plus use all by itself on one line. Don't do anything else to avoid any confusion. But anyway, if I do plus plus then IT, well, same idea. It's going to simply move this iterator over to the next node. That's the idea. So, of course, you could do minus minus, which would move it to the left over by 1. You could set the iterator, like right here, you could set it equal to lst.end and then do it minus minus. It's up to you. But you can see here, this iterator gives you a flexibility to move through a linked list, just like with a pointer, but we kind of hide the pointer data. We don't expose it. This star operator is really, we're overloading the star for the iterator class. We're not really using that built-in star operator over here, at least not at this level. Now, internally, it's using the arrow operator, which is being used right here, but this is just going to be a call to this operator function right there. So, of course, if you want to traverse the entire linked list, another way you can do this, so I also have this also in my notes in the PDF, but I want to kind of interactively show it to you. So you also could do this. So I'm going to create another iterator. I'm going to call it nil. So right there, I use a default constructor to create this. So this nil iterator, its current contains null pointer. So we're going to treat this as a null pointer when we're traversing through a linked list. So if I want to traverse the entire linked list, what I could do is I could say something like it equals lst.begin. And then while it is not equal to nil, we're going to run this loop code. So really, this is very similar to the basic way of traversing a linked list using a pointer, except iterator. But, I mean, same concept so far. Then I can do cout star it plus plus. And once it does equal nil, it will stop looping. So we're using this operator I wrote for you, this not equals, is being used right here. We're comparing if it's current is not equal to nil's current. So nil's current equals null pointer. Once you go beyond this node's 1, as you know, with doubly linked list, the tail node's next always contains null, and head previous always contains null as well. So once you hit that null, then this is going to be false, and it will stop looping. And of course, you can also have a for loop as well. Either way is going to work. It's up to you which you want to use. But you could use the following technique. Try to fit it here. I guess I won't be able to fit it here in this one frame. So I'll two-line this. And cout star it. So either loop is good enough. It's entirely up to you which one you want to use. But really, all we're doing iterators, all we're going to do with this is just traverse a linked list. That's all. So it gives us the idea, it gives us the option to traverse it like you would a regular pointer. So of course I gave you some code or gave you some writing in the PDF, but hopefully this explanation also helps. So now I'm going to go over those funky tail insert remove functions to give you an idea of what I want you to implement, and also you can see how this has a better runtime than if you were to use an array or a vector. Okay, so consider these two linked list objects I declared right here, and suppose I did a few tail inserts, the regular tail inserts. So this tail insert function, one here with my mouse, you can see it here in the mouse, but this tail insert function, let's say I called several times. So I inserted 3875 into list 1. I inserted 14 into list 2. So we have these two linked lists created. Now, in a solitaire game, you're going to have to often move a card or a set of cards in a chain or in a list or in a linked list, if you will, from one stack to the other. So let's say, for example, I want to move these cards. 875, I want to take these and put them right here. Now, the beauty of a linked list is I don't have to deep copy actually tail insert 8, tail insert 7, and tail insert 5. Now I could do that into list 2 to insert 875, which will essentially move those, but a linked list, I could simply just take the nodes 875, just pick it up, and just simply insert it to the end of list 2 without doing this inserting one by one. So this method actually has a better overall runtime than just, one by one inserting a node, inserting 3 nodes one at a time to the back of list 2. So when you want to actually do this, what you're going to first have to do is the following. You want to have 2 iterators, the start and end iterators of the list you want to move into this position. So the first thing you have to do, well, I'm going to first go ahead and just say, I'm going to create 2 iterator objects. I'm going to say and I'll call it maybe I1 and I2. So we could say something like I1 equals lst1 dot begin, and then I'll do I1 plus plus. So then essentially I1 is going to point to that node. And to get the second I2 to point to the end, well, that's actually easier. I could just say I2 equals lst1 dot end. And it's going to set I2 right here. So what you want to first do is you want to cut off sort of these nodes. You want to cut these off from this list. So what you want to first do is say lst1 dot remove and pass an I1. Now, I1 is your iterator being passed into the function. So here's what you want the result to be after doing this remove. Essentially, what's going to happen is you're going to move the tail pointer to the node right before I1. So tail is not going to point here. So you want the tail node to point to the node right before I1, and then you want to cut it off. So you want to do this. You want to simply set this equal to null, and then set this equal to null. So essentially you severed that list 875 away from that node 3. So think of it like those old train cards, those old train movies, those old Western movies, if you will. And you simply remove a train card and it sort of So let's say you have like 5 carts, right? If you go in between 2 carts and you lift up that metal piece that holds the 2 carts together, then the train moves and the remaining carts sort of stay behind. I think that's how it works, right? Like, I don't know the actual words, but you've seen those in movies, I would imagine, or at least you've heard of those. So we're doing that. We're simply severing 875 away. Now that it's severed, I want to, of course, now just do lst2 dot tail insert, pass in I1 and pass in I2. So we're going to simply insert the nodes from I1, I2 to the back of lst2. Let me see if I can try to just sort of use some nifty one node tricks. We're going to simply do this. We're going to just, I'm going to zoom out a little bit so you can see this all in one frame. And we're going to simply do this. We're going to set this pointer to point to that node. I1's previous points over here. And then we're going to assign LST2's tail pointer to point over there. And then that's it. We're done. So notice there was no looping. There's no one by one copying nodes. We just simply severed between 2 nodes. So the remaining set of nodes are now removed from list 1, and we simply just insert it into list 2. It requires a couple of pointers to be reassigned. And notice, I mean, this has a very good runtime. It's much faster than it would have been to actually copy the 8, 7, and 5. Now, for a small size list, like of size 3, it doesn't make a difference, but for a big enough list, it makes a heck of a difference to do this. So that's what this tail insert is going to do. Now, this other tail insert function, this first one right here, is the same idea like the second one, except you're going to move only one node will kind of slide over. So let me go ahead and just sort of cover an example of where the other, this first tail. So I covered this tail insert function right here. Let me go over an example of what we call this first tail insert function, which only has one iterator. Okay, so suppose we have these 2 lists. So again, we declared 2 list objects. We did a bunch of a bunch of tail inserts to essentially construct these 2 lists. So let's say I wanted to move this single node, and I want to put it on the back of this linked list. So this is going to be the other tail insert function, the one that only receives one iterator as a parameter. So again, what you'd have to do is let's go ahead and create 2 iterators. Or actually, I would just need just one iterator for this one. So iterator IT. And if I say IT equals to list 1.end, then what happens is, of course, IT points to that node. So the first step, before we move this 1 over, we have to first sever that node 1 from the first linked list. So of course, what we can do right now is do a remove once again. So I would just say list 1 dot remove, pass in IT, which the end result is going to be that this node, the node 2, it will point to nothing or point to null, and then tail is now going to be assigned over here. And of course, IT, that node's previous points back to nothing. We set that to null. And then, of course, we would just do lst2 dot tail insert, pass in just IT. And end result is it's going to just simply, let's see if I can somehow get this to copy. Also, the pen is not working nicely right now. I cannot get this to highlight. Ooh, it's not highlighting right now. Okay, let me just see. Okay, for some reason my pen is not working correctly. It's okay there. So just pretend that I grab this. Yeah, actually, I think I can use a mouse maybe for this. Let's try to use a mouse. My mouse has been also acting up lately as well. Let me just try to. No, nothing. Okay, there we go. There we go. So what's going to happen now is we're going to move this over here. And then, of course, we're going to set the tail nodes next point here. IT's previous points back over there. And then we set the tail pointer right there to move that node over. So we use that if you're trying to move one card from one stack to the other. The other tail insert functions if you want to move a set of cards from one stack to the other. So you can see how we're going to use these two tail insert methods to kind of simulate a move in our solitaire game. Okay, so this is basically sort of the explanation as to how to implement the functions and how to use iterator and so forth. Let's now go ahead and discuss the solitaire game, how you want to implement that, and then of course give you some sort of final remarks before I end the video. Let's go ahead and get to it. Okay, so I guess kind of consider this image right here. So the idea is you're going to, well, first you're going to want to have maybe a struct to denote each card. So each data field of each node in the linked lists are going to just contain a struct card type to make it a little bit easier. So each card has a face from 2 to 10, and then the suit will be, well, spades, clubs, diamonds, or hearts, which we use letter S, C, D, and H respectively for each of them. And of course, we're going to have an array of 5 linked list objects. So each of these will be an element of, so this will be piles index 0, piles index 1, and so forth. Each element of this piles array is going to be sort of a linked list object. Now I think here in the PDF I made a small mistake actually, because this could be ambiguous because I guess it's uppercase letter. I guess uppercase, lowercase shouldn't cause any issues, but again, probably use better variable names just to be safe, I guess. But you get the idea. So we're gonna have an array of size 5 for our solitaire game. Then we're gonna have an array of 5 iterators. So notice right here, these red arrows are going to be our iterators. So this tells us the top of each stack. So we're going to reveal this card to the screen, and let's look at this sort of stack or pile for right now. This card, we're going to show its face, but since these cards right here in this stack appear before the iterator, we're going to just simply denote, we're going to show maybe 2 underscore characters to denote that it's turned over. So anything that's going to be at this position or further to the right will be revealed. Everything else will not be. So the idea is we have these 5 iterator objects, and of course as we move cards around, we're going to decrement iterator by 1 card up. So when we move a iterator up 1 level, then this card will now get revealed. So for example, if for some reason I want to move, let's say, this card to, let's say, this stack, then of course we're going to update this iterator to now point over here. And of course this card, I'm sorry, I think it's going to be over here actually, sorry, over here. And then of course we wipe that address out. So the idea is that these 5 iterators only display the kind of the first card to be revealed. So over here in this pile, since this iterator appears pointing at this node right here, we're going to display this card's face and this one too. But any card that's before the iterator is not going to be displayed. So that's going to be considered a turned over card. But as we move cards around, we always move the iterator 1 to the left, or in this case 1 up. So that way the card that was below, the very topmost face down card will now get flipped over, if you will. So all we're going to be doing is constantly doing tail inserts. We're going to be moving either 1 or more cards from one pile to the other. So for example, if, let me just sort of go back for a second. See if I can do this. I think this should be good. Okay, I think it's good. There we are. So, for example, we only move this card into this stack only if this card is exactly one less and it's of a different color. So, for example, diamonds and hearts are red, spades and clubs are black. So make sure they're different color, and of course we can move it. And of course, once we do move one or more cards from one stack to the other, then that iterator from that particular pile, that iterator moves up to the left or moves up one or to the left one, which will now expose a new card on that stack. So if you go back to just playing the regular solitaire game, you can kind of see like what the point of that is. So if you move this card, like I did a second ago, if you move this card over into this stack, then we have to move this iterator up once. Now this card that was turned over is now going to be revealed. And of course, if you have two cards here, I can move both of these cards to different stack potentially if that's what happens. So again, I'll let you kind of work out the code and figure it out. I do actually have some writing here in the PDF for you, but of course I'll let you kind of figure this part out. So these are going to be the actual sample runs I'm going to give you. So here's a first simple one. So right now, initially, here are all my cards. Let me show you what the init file contains. So you're going to be using what's it called? You're going to be using a command line argument to read into file name. You open up a file stream to actually read this set of cards into your arrays. So let me go ahead and just show you this right here. Let's see, there we are. So the input file, the first stack contains one card, 10 of hearts. Next stack is going to be 10 of spades, 4 of diamonds, and the next one 7 of diamonds, 8 of diamonds, 6 of diamonds, and so forth. So you can see this. But of course, only the topmost card in each stack will be revealed currently. So now what will happen is, let's say when I say 5, 2, that means card in stack 5 goes to stack 2, so 3 of clubs can be moved at 4 of diamonds. So what happens if we do a tail insert, we put 3 of clubs right there, and notice that since this card was moved, our iterator moved to the left by 1, so the card right before 3 of clubs, which was 7 of clubs, is now revealed. As we progress through this, let's see if we can find a more interesting scenario. Here we go. So we have, let's say, in this step, we want to move a card from stack 5 to stack 3. We take these cards, 7 of clubs, 6 of diamonds, and you move that entire stack over here. So now 8 of diamonds, we tacked on 7 of clubs, 6 of diamonds. And of course, the iterator moved over to the left by 1, revealing 9 of diamonds next. And we keep this game going until we finally have all of the cards exposed. Then the game is over. Then my second run, same thing. I pass in the file name using a command line argument, and I pass that file name into a file stream, and I read in, the initial cards, sorry. And of course, I interactively read in the input. So that's what you want to do. Now, next, a pretty important part, I want to go over exactly how you want to display the output so CodeGrade is going to be okay with it. So essentially, I'm going to give you guys the complete input. So for example, I'll give you this. I'll give you a set of input files you can use to test your program. Now, you're not going to want to actually type these numbers in one by one. You're going to want to use a Linux redirection to read in the file into your program. But when you do that, it's not going to actually display the input on your terminal. So let me go ahead and show you how that works, and so you can see how that works. So of course, to make it a little bit easier to check the output on CodeGrade. So the last important step will be right here in the video. Okay, so from the sample files I give you, I do have a separate header file and implementation file, but in order to get them to compile and link them separately, I had to do some really weird tricks. So to compile your code, you have to simply just type in G++. I'm going to use main.cpp. Okay, So I'm going to go ahead and use this input. I'm going to put it here to this. Sorry about that. My mouse is really weird. It actually double clicks my single clicks sometimes. Probably I should buy a mouse soon, but oh, I keep forgetting about that. So anyway, if I run my program, I'm going to go ahead and, pass in the input file like this. Okay, it displays all my stuff. I type and say 5-2. So from pile 5 to pile 2, so 3 of clubs will get moved into 4 of diamonds. So you can see that it moved over there, and this card, now the card below, right before, is now displayed, and so forth. So of course I type in 4-1. It's going to go ahead and sort of simulate the next move. So there's 9 of clubs, went to 10 of hearts, and so forth. So again, you can test it out like this, but this is a little bit redundant if you want to test it out many times. So a better approach, instead of actually typing this whole thing out character by character, a better move would be is to simply feed this file into your standard CIN, your standard input. So you might learn about this maybe 135, but if not, I'll go over with you right now. So I'm going to go ahead and just close. I'm going to Control C to terminate this. So what I can do is, once again, a.out. I'm going to pass in my file name, and I'm going to use this symbol right here. So this looks like it's pointing towards a.out. This is known as an input redirection. So from now on, the CIN is not going to read from the terminal what I type, it will read it in from a file. So the file I provide is this file right here. I want to feed the entire file automatically into CIN. So I'm going to go ahead and just say input 01.txt. And what happened was it just automatically fed these inputs. Every time a CIN occurred, it just read from this file automatically. Now notice this. See how above I have 5-2-4-1? Well, that's because I actually typed that into my terminal. But notice here, there is no 5-2-4-1 because it's not going to display it here because I didn't actually type that. So in this case, whatever my program outputs is the only thing that's going to be displayed right here. So a workaround is to simply just output what you just read from CIN. And that way it will display everything that was read from this input file. And in fact, on CodeGrade, that's what we're going to do. It makes it easier to see which inputs might have caused problems on CodeGrade for you. It's easier for you to help you figure out what's going on. So all you have to do is simply just see out wherever you CIN, just to make things a bit easier. So that way it will display what was read in. I'm going to go ahead and sort of uncomment that uncomment that part of my code. Let me go ahead and just sort of recompile this so you can see what's happening. I'm going to do G++ main again, init, and then I'm going to go ahead and do this again, input 01.txt. And look, so right here, all I did was I CIN'd these two numbers, and I simply output them. So the input in this program will be just simply, you will be read in sort of a pair of numbers, a from to to. So from pile 5 to pile 2, from pile 4 to pile 1, and so forth. But I simply output what I read, so it displays the actual input on my terminal. So it's easier to see what input was being read at any given point in time. It also makes it easier on CodeGrade to verify where in your program which inputs might have caused some differences issue on CodeGrade. So all you have to do is, when you read in these two numbers, just display them. Now, if you were to do that and not redirect the input, so suppose I just run this once again. I'm going to clear this terminal out. I type in init. Let's see if I go ahead and type in 5-2. Notice the display is 5-2 again. But it's not a big problem. If you wanted to actually do it manually, I guess you have to kind of deal with double outputs, or you can comment out that code for a little bit. But the idea is that if you're redirecting, maybe it's good to output what was read in, so it's easier to see what what the output is. So on code grade, in fact, you want to make sure you output what the input was, or else code grade will mark yours wrong. But it's a very simple fix, actually. So also what I give you guys to work on. So let me just go ahead and give you some more. Let me show you some more to test code. But I give you guys 3 input files and the respective output files I will provide. But I also provide you guys with a couple of other let's see, I'm going to go ahead and a couple of other source code files. So I think I provide these. So I provide these for you. So on CodeGrade, I'm going to sort of link your your linked list file to different mains to test out your code. So that way, instead of only giving you points just for a solitaire game, I'm also going to give you points just, these are going to be almost like kind of a unit test. It's not our unit test really, but I guess, it's going to be our version of that for right now. This file will test out to make sure that your tail insert function works correctly. This file I'm going to use, it's going to test out to make sure that you did write your copy constructor correctly. This file is going to test out that really weird tail insert, that iterator based tail insert. I'm going to have this file test that out. It's actually very good to use this because you can make sure if this is working correctly, then of course you can then proceed and continue to work on the solitaire game. So if let's say these files, especially if this and this, if these work correctly, then you are ready to begin working on solitaire game, because you want to make sure that your tail insert iterators works before you can even attempt to even try solitaire. So anyway, that's sort of the idea I guess that's sort of my explanation for this assignment. Hopefully this video helped to get an understanding of it. So yes, happy coding, and until next time.